The chemical substance benzene, which is aromatic hydrocarbon, might not be a household name, but we encounter it more often than we think. It is involved in various industrial processes for its unique properties to manufacture products we use in daily life. Like plastic, dyes, glues, it is one of the most important components of gasoline also. But do you know, seemingly trivial changes in the structure of carbon ring can completely change the chemistry of the molecule. Yes, benzene and some polynuclear hydrocarbons containing more than 2 benzene rings fused together are toxic and said to possess carcinogenic property. These polynuclear hydrocarbons are formed on incomplete combustion of organic materials like tobacco, coal, and petroleum. They enter into the human body and undergo various biochemical reactions and finally damages DNA and causes cancer. In this video, we will discuss a few important properties of aromatic hydrocarbons. Let's start with the physical properties of hydrocarbons. Aromatic hydrocarbons are nonpolar molecules and are usually colorless liquids or solid with a characteristic aroma. It is immiscible in water but dissolves in organic solvents. If you burn aromatic hydrocarbons, it burns with a sooty flame. Aromatic hydrocarbons are expected to behave like unsaturated hydrocarbons and must be reactive chemically. They show characteristics similar to that of saturated hydrocarbons, that is alkane. They are characterized by electrophilic substitution reaction. However, under special conditions, they can also undergo addition and oxidation reaction. The common electrophilic substitution reaction shown by aromatic hydrocarbons are nitration, halogenation, sulfonation, Friedel-Crafts alkylation and acylation reaction, in which the attacking reagent is an electrophile. Let's discuss each of them in detail. Nitration of benzene is done by heating it with a nitrating mixture of concentrated nitric acid and concentrated sulfuric acid to about 323 to 333 Kelvin. As a result, a hydrogen atom in the ring gets substituted by a nitro group. The nitration is carried by nitric acid while sulfuric acid is added to catalyze the reaction. While in halogenation, benzene reacts with halogen in presence of Lewis acid like anhydrous ferric and aluminium salts. These Lewis acids carry halogen to the aromatic ring. Here, a hydrogen atom in the ring gets substituted by the halogen. Well, in sulfonation, the hydrogen atom in the ring is replaced by a sulfonic acid group. It is carried out by heating benzene with fuming sulfuric acid to give benzene sulfonic acid. In Friedel-Crafts alkylation reaction, benzene is treated with the alkyl halide in the presence of anhydrous aluminium chloride to give alkyl benzene. Here, the hydrogen atom in the ring is replaced by a alkyl group. Whereas in Friedel-Crafts acylation, the hydrogen atom in the ring is replaced by an acyl group. Here, the reaction of benzene with an acyl halide or acid anhydride in the presence of Lewis acids like AlCl3 yield acyl benzene. But do you know what reaction mechanism do these reactions follow? Let's discuss them. According to experimental evidences, electrophilic substitution reactions are supposed to proceed via the following 3 steps. The first step is generation of electrophile. Second step is formation of carbocation intermediate. Third is the removal of proton from the carbocation intermediate. During chlorination, alkylation, acylation of benzene, anhydrous AlCl3 being a Lewis acid helps in the generation of electrophile chloronium ion, R plus acylinium ion respectively by combining with the attacking reagent. In the next step, The attack of electrophile results in the formation of sigma complex or uranium ion. The uranium ion gets stabilized by resonance. Next, to restore the aromatic character, sigma complex releases proton on attack by AlCl4- ion in case of halogenation, alkylation and acylation, and HSO4- in case of nitration to form the desired product. As discussed, under special conditions, aromatic hydrocarbons can also undergo addition and oxidation reaction. Well, under vigorous conditions, that is, at high temperature or pressure in the presence of nickel catalyst, the hydrogenation of benzene gives cyclohexane. And under ultraviolet light, 3-chlorine molecule adds to benzene to produce benzene hexachloride, that is C6H6Cl6, which is also called gamexene. Whereas benzene undergoes combustion and burns with a sooty flame, producing carbon dioxide and water when heated in air. In monosubstituted reaction of benzene, only one monosubstituted product is formed, as all the positions of the ring are identical. But in case of disubstitution, 3 isomeric products are formed, that is ortho, meta and para. It may be noted that the group already present in the ring directs the new group to a particular position. This is known as the directive influence. In general, the group has been classified into 2 types. One is the ortho and para direction group and the other is the meta directing group. Let us discuss the directive influence of phenolic group. Phenol is a resonance hybrid of the following structures given. Here, the substitution mainly takes place at ortho and para position, and the electron density is more on these positions. However, it may be noted that -I effect of OH group also operates, due to which the electron density on ortho and para position of the benzene ring is slightly reduced. But the overall electron density increases at this position of the ring due to resonance. Therefore, OH group activates the ring for the attack by an electrophile. The common example of ortho and para directing groups are amino groups, acyl amido groups, alkoxy groups and alkyl groups. In case of aryl halide, halogen are moderately deactivating. Because of their strong -I effect, overall electron density on benzene ring decreases. It makes further substitution difficult. However, due to resonance, the electron density on ortho and para position is greater than that of meta position. Hence, they are also ortho-para directing groups. Thus, we can say that group which directs the incoming group to ortho and para position are called ortho-para directing group, whereas the group which directs the incoming group to meta position are called meta directing group. Some examples are given here. Let us take an example of nitrobenzene, which is a resonance hybrid of the given structures. Here, nitro group reduces the electron density in the benzene ring due to its strong -I effect. Thus, the electron density on ortho and para position is comparatively less than that of meta position. Hence, the electrophile attacks on comparatively electron-rich meta position, resulting in meta-substituted product. With this, we came to an end of this video. Now, can you tell me what is the role of catalyst in the electrophilic substitution reaction in benzene? Well, try to figure it out. Let's now summarize what we have learned.
Manorama Horizon. Learning made simple.